In this video, we're going to be discussing the basics of chemical bonding. This is a topic we're going to cover in a lot more detail later in the year. For now, you should be familiar with some different types of bonds that are out there and how they're going to play out in the next couple chapters. We'll start with a quick overview of what's going to happen here. We're going to start with a talk of what an actual chemical bond is, something I feel like you should have seen before but might require a little bit of a refresher. A question you might not have answered before is a little bit about why chemical bonds form. And again, as we learn more science throughout the year, we'll be able to answer this question in better and better ways. And then lastly, but most important, right down here, we're going to talk about the different types of bonds. In the next couple chapters, you have to work with the different types of bonds, even if we don't understand all the mechanics. Understanding what those differences are from bond type to bond type is the information we're going to need for now. Before we move on, just kind of give an idea of what we're talking about. Over on the right, we have an image for a molecule showing the caffeine. Both of them are caffeine. As we can see, one of them showing a two-dimensional version of this, a flat picture here, whereas we have a three-dimensional rendering. Both of these are depicting chemical bonds in action, linking multiple atoms together in order to make what we refer to as compounds. Well, let's start our discussion then in terms of what an actual chemical bond is. In short, it's an attractive force between two atoms that links them together, causing them to behave as one new substance. And we have a name for this one new substance. This is something we refer to now as a compound. This linking of atoms, or this connection here, causes changes in the arrangements of electrons around each individual atom. And by changing these arrangements of electrons, we're causing a couple different things to happen. First off, this changes in electrons results in a better, more stable orientation of those actual electrons. And as we've seen in the previous chapter with nuclear stability, a more stable result is something that atoms are always moving towards. Likewise, this changement of arrangement of electrons also completely changes the physical properties and the chemical properties of our newly formed substance. Because the electrons are oriented differently, the substance itself behaves differently as well. So then what we can talk about then, now that we know what a bond is why do these chemical bonds actually form? And we've already kind of touched on this a little bit. All things in our universe naturally move or change in order to gain a lower energy state or become more stable. And this is a topic that comes up in physics, it comes up in chemistry, it comes up in biology. It's one of the governing forces in our universe itself. As some really quick examples, we can all think about being at a roller coaster. Being at the top or the apex of the roller coaster is an unstable situation. It's a very high potential energy state. And as naturally, what our roller coaster car is either going to naturally fall down this way or naturally fall down that way. No matter what you do, left at the top of this hill long enough, those roller coaster cars are eventually going to come down. Same thing's true in chemical reactions. Enthalpy is a form of energy that we'll be dealing with later in the year. We can see reactants such as the sodium ion and the chloride ion have higher energy and naturally combine together to create the lower energy product of sodium chloride. Again, this is the discussion for later in the year for details, but for now we can see how the same forces that drive the roller coaster to go down the hill are the same forces that drive chemicals to combine in ways and form bonds to create our compounds. So to summarize then, when an element can combine with another element or elements in order to create a new configuration of electrons that is lower in energy and therefore most stable, a reaction will naturally occur, and maybe we'll add that word in here. A reaction will naturally occur forming those new chemical bonds to create that new lower energy substance. So to pull it all together then, just so we have one statement we can walk away with here, is that atoms will form bonds with other atoms in order to get better, more stable configurations of electrons. I think we have a lot of talking to do later in the year about what these configurations are and which ones are or are not stable. But for now, this is a justification for us for why these bonds are actually formed. This can be done in a couple different ways then, and this is how we're going to transition into the second part of our discussion. Forming covalent bonds, and hopefully, by the way, these are words that are familiar with you, is one way that atoms can link together in order to get these more stable configurations. Forming ionic bonds is a different way of doing this. The goal is the same, the better configuration, but the methodology for doing it with an ionic bond is different than the methodology for doing it with a covalent. And last but not least, the one we'll talk about the least this year, are dealing with coordination bonds, a different type of covalent bond, and again, gets to the same goal. These types of bonds involve much more complex representations of electron configurations, but again, the goal is the same of getting to a more stable configuration. The remainder of our video then is all about talking about the three different bond types. More than anything, your job is to be able to identify those bond types when looking at the chemical substances that you'll be working with in the next couple chapters. The first type of bond type we'll talk about will be covalent bonds. In a covalent bond, the key word you want to focus on here is the one I have capitalized. Atoms share electrons in order to get better electron configurations. Basically what happens in a little more detail is that pairs of electrons are shared between two atoms, and this allows both of these atoms to count these electrons as part of their own configuration. The bond then, the thing that actually links the two atoms together, and this bond, as we already said, is an attractive force, comes from the electromagnetic, and that's what EM stands for, the electromagnetic pull from the nucleus, which has a positive charge, on the shared electrons between the two atoms, which have a negative charge. So the positive charge on both atoms is pulling on those shared electrons, and that holds the atoms together. So let's talk about how to recognize when covalent bonding is happening. Covalent bonds occur when both atoms need to gain electrons, and maybe we'll add that word in there to be a little clearer. When both atoms need to gain electrons, we typically see a covalent bond, and when neither atom has the sufficient attractive force to pull the electrons off of the other. The end result is that they're forced to share the electrons. Something you can do to simplify this a little bit, and we'll talk about these forces later in the year. Covalent bonds occur when a nonmetal substance bonds to other nonmetal substances. Both of these substances have very strong attractive forces, and they end up canceling each other out. So the net result is neither substance can pull the electrons off the other. The result is sharing of electrons. Let's move on to bond type number 2 then, ionic bonds. Again, a bond type I think you've heard before in the past. In ionic bonds, the key term here isn't sharing this time, but now there's an exchange of electrons, causing one atom to lose electrons and the other atom to gain electrons. When you do this, you create atoms with charge. And the word we use for that is the word ion. And an ion is basically defined by being a charged atom. The atom with the positive charge is the one that must have lost electrons. We have a special word for that in chemistry known as a cation. This is a term that will come up a lot in class, especially when we're dealing with electrochemistry later on. The negative ion is the one that must have gained electrons. It has extra negative charge, which is the charge of an electron. And these guys we refer to as being the anion. Again, a term we're going to use regularly, especially when dealing with electrochemistry. Again, the whole goal here is to talk about what the bond is, or what the attractive force that actually results in linking the atoms together. And again, it's an electromagnetic force. But now you've got a much simpler situation. You've got a positive cation, you've got a negative anion, and naturally, as we learned from physics last year, those opposite charges are going to attract and those atoms are going to be held together. So to wrap up ionic bonds then, these occur when atoms need to, again, change their configurations in a particular way, specifically when one atom needs to gain electrons and the other atom needs to lose electrons in order to get to that more ideal configuration. This also happens when one atom has a significantly stronger pull than the other atom does on electrons, in which case one of them takes the electron from the other. To summarize, the thing you're going to need to know is this statement down here. These types of bonds occur when a metal substance bonds to a nonmetal substance. Those nonmetals have a very strong electromagnetic pull. Metals tend to have a very weak electromagnetic pull, and as a result, the electrons tend to get pulled from the metal onto the nonmetal, creating a negative charge here and a positive charge here, thus making our ionic bond. Last but not least, coordination covalent bonds. This is not a bond type I expect that you need to know a whole lot about other than what it actually is. I bring this up simply because we'll be dealing with some coordination complexes, and I just want you to be able to recognize what it is we're talking about. These are actually bonds that form between molecules themselves, and typically there's a larger molecule, and then that connects to a certain number of smaller covalent molecules. So you get one large molecule collecting to many smaller, and like before, these things have names. The larger molecule we often refer to as being the coordination center, and then the smaller molecule, and there's usually just one of these. And then the smaller molecules that are connecting to it, known as the ligands, there's typically many of these, although not necessarily always. It is a type of covalent bond, and it's a type of covalent bond that forms between the metal in the coordination center and any particular atom in the actual ligand itself. And there's a whole lot of chemistry that goes behind how and why this happens. That's beyond the scope of what we're going to be covering in this class. In some cases, one of the ways we can characterize coordination bonds, these bonds tend to be more easily broken. And you've actually already seen this in an example we're going to talk about in a second. Now, in recent studies, there have been shown there are some coordination covalent bonds that are just as strong as regular covalent, but generally speaking, these types of bonds are more easily broken than other types of covalent bonds. So just like any type of bond, a coordination covalent bond does indeed involve the changes in the arrangements of electrons, but these changes are much harder to see with the models that we're going to be talking about this year. And as a result, we typically need much more complicated models of electron configurations in order to understand why a coordination bond improves an electron configuration or an arrangement of electrons. What we can say is where these things actually show up in. And the example that we're going to be dealing with primarily this year is in the form of hydrates, one of the chemicals you're going to be responsible for knowing about. A hydrate, for example, the one we're showing here is copper sulfate, and we draw a dot here with 5H2O, showing that there are 5 H2O ligand molecules attached to the coordination center copper sulfate. We can see 4 of those water molecules attached directly to the copper atom itself, and then 1 more of them attaches to the sulfate ion, which we're going to be learning about in a couple of days. As a result, we have 5 water molecules attached to our coordination center here, and this is an example of a coordination complex, which is what we would call this whole structure. This also shows up very commonly in biological molecules. This big model right here is a sample or part of what we would describe as a hemoglobin molecule. This is what carries blood in our body, and as we know, the job of hemoglobin is to carry oxygen throughout our body. The iron here at the center of this hemoglobin acts as the coordination center, which allows these oxygen molecules to attach onto it. This transports the oxygen to parts of our body that needs it, and then releases it at the appropriate place, picking up other things like carbon dioxide. All right, so that's it. Let's talk about a rundown of what it is you guys should be able to do at this point. You should be able to define what a chemical bond actually is. You should be able to explain why atoms actually form bonds, what the reasoning is behind that. Again, both topics we're going to cover in a lot more detail later in the year. You should also be able to define and describe the different types of bonds themselves, specifically focusing on covalent and ionic bonding. Coordination bonding you should be familiar with, but really all we want to be comfortable with is being able to describe and understand what a hydrate actually is. Last but not least, and this is probably the most important part of the process, you should be able to identify the type of bond that's present in a substance. You should be able to look at a formula and say, this is an ionic compound or this is a covalent compound. That's going to be very important for us when we work on naming in the near future and when we deal with other types of bonds and reactions in the future after that.